by Gabor Martin and Daniel Krupp, who will also be taking questions afterwards.
We created the CodeChecker project in 2013 to replace expensive commercial C and C++ static analyzer tools with a free, open source alternative. We chose analyzers from the LLVM Clang infrastructure to be the engine of the analysis. CodeChecker drives these engines and stores the results in a database so we can browse and administrate the analysis findings. I am Gabor Marton. I work in Ericsson, Hungary in the CodeChecker team. We chose Clang back in 2013 because it had an up-to-date C and C++ language support. It had and still has a permissive license, so we could easily extend it to our needs. The Clang analyzer supported path-sensitive analysis. It modeled the C language quite well. We found its memory modeling pretty mature, and it had an active developer community, which is even more active now. This slide represents the architectural overview of the CodeChecker tool. There is a command line interface which drives the analysis. There are many different build systems and compilers within our company, so we provide one uniform interface for the users to analyze their projects. There are analysis options which require multi-phase analysis. These phases are executed by the command line scripts. The primarily supported analyzer engines are the AST matcher-based Clang tidy and the path-sensitive Clang static analyzer. Our team is an active contributor in these components. We continuously add new checkers and fix bugs. The results are stored in a database, and with the help of a web server we provide dashboard functionalities. Developers can follow each step of a path-sensitive bug report. QA managers can have a good overview of the errors, including their type or severity. They can check how many reports are associated with a specific software module, or they can follow up trends about the number of new or fixed errors per release. Also, analyzer developers may gather information about suppressed checkers, and this could be really useful for them to identify false positive cases for a specific checker. CodeChecker provides integration to code review loops. In case of a new pull request, the developers can see if there is any new report introduced by their change. They either fix the new bugs, or in case of a false positive, they may be able to suppress the report. We provide the possibility to store reports from other analyzer engines as well, for example from Facebook Infer or from CPP Check. However, these analyzers must be executed manually by the users. The CodeChecker command line executes automatically only the Clang analyzers. Our main contributions to Clang were that we added cross-translation unit analysis, we added several new checkers, and we improved the report messages. The Clang analyzer was capable of doing inter-procedural analysis by the means of function inlining. This technique, however, was confined within the boundaries of one translation unit, so we added cross-translation unit analysis, which is the natural extension of the function inlining technique, but we can get the definition of a function from any other translation unit. There are many C and C++ specific checks that we have implemented. Our efforts were and are still guided by the CERT Secure Coding Guideline, which formulates security-critical rules. These are C++ iterator and container checks, or checkers related to memory access. In this slide, you can see the progress we made with the number of the passing CERT related tests over the years. Here we display the coverage of the different CERT rule groups. This is the current state with the latest Clang release, which is Clang 10. Many error reports were hard to interpret, so for elevated user experience we tried to improve the analyzer messages. This is our third contribution. Here is an example for the improved warning messages. At the left-hand side of the slide you can see the warning report before the improvements. The right-hand side displays the improved report. In this example, there is a global variable flag, which is set to a random value in the for function. In the bar function, we initialize the x pointer to null, and then at line 12, the flag gets a random value. At line 13, if flag is 0, then we don't call new, so x remains null. Next, at line 16, flag has a new random value, and if that is non-zero, then x is dereferenced. But that is a null pointer, so we receive the warning. In the old version, we did not display to the user that there is a value assigned to flag in the foo function, and that value actually participates in a condition later. As for the future, we plan to open source our statistical checkers, which are based on the idea if the return value of a function call is handled at 90% of the cases, then it's an error not to handle it. We would like to further refine the taint analysis capabilities of Clang. Also, we plan to implement some form of summary-based analysis. We are hoping that with summary-based analysis, we can achieve a good balance in between precision and scalability. Naive inlining can be absolutely precise, but the computing resources may be depleted easily, even with a shallow call stack. By using summaries, we plan to model complex functions with a simpler alternative. A summary could contain information about whether a function is pure or about the range of the return values. First, we'd like to make it possible to manually add summaries to the most important library functions. For example, functions from the standard C library or functions from the POSIX standard. Then the next step would be to automatically generate summaries for certain functions. For this, we are planning to reuse already available data flow frameworks in the LLVM universe. And now, Daniel is going to demonstrate the use of the tool.
Hi, I'm Daniel Krupp, a CodeChecker developer at Ericsson. Let us demonstrate the cross-translation unit analysis feature on the open source terminal multiplexer project. First, we need to capture the compilation into a compilation database. We can use the CodeChecker's log facility to do that. When the logging phase finished, we can start the analysis. We switch on the cross-CU flag, and we run the analysis on 20 threads. The reports will go to the report CTU directory. The first analysis phase just finished from the two-phase analysis. After the analysis is completed, we can upload the results to the web server. We can use the CodeChecker store commands to do that. We'll store the run under the name tmux-ctu. After uploading the analysis results to the server, we can investigate them and compare them. The first result set is called tmux baseline, and it is without the cross-TU analysis. The analysis consists of 98 reports, contains 136 files, and completed in 44 seconds. The second is tmux-ctu run with cross-translation unit feature. It has a considerably more number of reports, 260, but also the analysis time is 3 times longer. With the CodeChecker diff feature, we can compare these two runs and see which are the new results in cross-translation analysis. And then you will see we have 77 new findings. Among these new findings, there are many severe errors like null pointer dereference, division by 0, or uninitialized branch. If we click on the first new finding, we will see a long bug path rendered over the source code. We also see that the bug or the problem pointed out by the analyzer is access to field window through the VL pointer, which is null. And this will cause a crash in our program. We see that the whole control flow started out from server fn.c, and then through steps, it goes through session.c, over to notify.c, and finally it ends up in command find.c. If you'd like to see an overall overview of the findings from your project, you go to the checker statistics page, and there you see which checkers found the most errors in your code. In this case, in this small project, the Clang diagnostic pointer sign checker found the most number of bugs, and the second highest number was the Unix malloc checker. As you saw, it is worth to try out the cross-translation unit analysis, because you may find severe bugs in your code at a cost of higher analysis time.
Thank you very much. So now we have the opportunity to ask Daniel Krupp and Gabor Marton about their CodeChecker system, or generally their industrial perspective on matters related to code checking tools and their experiences with how the various tools that they've mentioned, including Clang, Tidy, and Info, might apply in practice. We already have two first questions. And the first one is from Lingua Duo, which is, were the red arrows on slide 15 to visualize the witness path for the bug?
Yes, actually, those, yeah. So we display their bug passes, and each of those red arrows are edges between the nodes of the bug paths.
Yeah, so they represent the control flow. Actually, Clang Static Analyzer does a symbolic execution. And then, so yeah, it is practically a witness. So it points to the programmer that how the program produces the actual error undefined behavior.
Thank you. The next question is from Andrew V. Jones. Are the kinds of errors you find richer than what Sarif supports? Could you use your visualization to display other errors if they are in Sarif format?
Yeah. Actually, we haven't compared Sarif format. We use in the CodeChecker tool the Apple plist format, but we could also just add, I think, Sarif format. We didn't compare in detail the capabilities of Sarif, but I guess Sarif format can also display a control flow. So to an error report, it can associate a control flow as well, as far as I know.
Thank you. The next question comes from Lingua again. She asks, are the bugs only shown on a web page, or do you also have IDE integration?
We have an IDE integration to Eclipse. Yeah, sorry, Daniel, please.
Yeah, exactly. So as Gabor said, Eclipse integration is ready. And also, of course, you can display the error reports in command line or static HTML. And we're thinking about providing an LSP, so language server protocol integration. But for that, for this full control flow visualization, we may need to extend the LSP protocol itself as well.
Thank you. She asks whether you also have these arrows in Eclipse then.
Eclipse, I think not arrows, but the bug path is visualized as a tree, I think, and then you can click on the tree elements and then it will jump in the source code to the point. So it's not exactly arrows.
Okay, thank you. I think we are about done time-wise, but I would recommend you to stay tuned to listen to her later talk, where I believe she might be discussing some opportunities to speed up LSP support for your purposes. So thank you very much.